All right, hello and good morning. So today we're looking at our first class of equations that we're going to solve. We're going to solve these by hand, and this will kind of drive a lot of our other methods and how we understand to to come up with solutions. All right, so we're starting simple, and it all kind of revolves around the exponential equation, which is why you might have heard myself and maybe other professors at this college, if you've taken Calc 1 here, we really bang on the exponential function and its derivative and its integral so much because so many of our solutions in this course revolve around that function. It's uniquely tied to differential equations. But I don't want to overplay that too much right now. What we're going to do is unpack again some of the definitions. I'll show you some examples, and then I'll show you the general method for solving equations of this form. And so this will work as long as they're of this form. Okay, so that's one thing that we can guarantee. What form is that, you ask? Well, that's if we can write a differential equation. And it's got to be an ordinary differential equation. What do we mean by ordinary again? It means that it has just one input. Okay, so if we can write that a differential equation like so, where we have u prime of t equals some forcing function or input plus h of t times u of t. Okay, noting what these are all functions of. They're all functions of time. Then we know, sorry about that, then we know, one, that it is linear. And what does linear mean again? It means that u only appears, our unknown function only appears in powers of 1, exactly 1. Kind of analogous to what you remember from static equations being linear. U only appears with a power of 1. So as you can see here, g of t, that's a function of t. There's no u's here. H of t, that's a function of t. There's not going to be any u's here. U of t, right, this will be u as a function of time. This can have a u, right? This can have u or be u, but it won't have anything that is not a power of 1, all right? And the left-hand side is obviously du dt. So if you can write it like this, it's linear, which means if you can't, it's nonlinear. All right, and we should just know, even though we might not understand fully what I mean by this, that nonlinear differential equations are, way more complicated in general than linear. Okay, so that's why we're starting with linear. So that's one thing that we know. Another thing that we know is that g of t equaling 0, so that what we call that forcing function, this implies that the equation is homogeneous. Okay, so if we don't have this guy and we're just equal to some h of t times u of t on the right, then we call this a homogeneous equation. All right, which also, again, simplifies things greatly. If not, this implies what we call non-homogeneous. And lastly, my final note here, is that if h of t equals some k where k is a constant, then we call it a constant coefficient equation. And if it's a function of time, then it's a non-constant, or what we call a variable coefficient. All right, so I may have made this comment before, but the reason that we have all these different categories and classifications of things is because solving differential equations is so freaking hard. So we need to be able to categorize the different types so that we know how to attack them. All right, another bit of notation here is that you might see is, that you have u prime is a function of t and u, where all of the other considerations I just laid out are true, where you don't see u in any other power except for 1. The coefficients you see, whether they're constant or constant, if you have a forcing term or not, all those things still hold up. This is just another simplified way to represent a first order linear DE. Again, if it is linear, in fact. Okay. So let's look at a few examples maybe that will help illustrate these points here. So if you remember the Hill-Keller equation, the sprinting model, this was v prime equals p minus k times v of t, where, p and k are constants. So, what do we know about this? Well, based on what we just said before, we have some things. We know that p is non-zero. Okay, so this tells us that it's non-homogeneous. We know that k is constant. That tells us that it's a constant coefficient. Again, all these things tell us eventually what tack to take when it comes to our method to solve. So that's why we're spending time doing this. And then we know that v only appears with a power equal to 1. So it tells us that this is linear. And we know that it's ordinary because we only have one input variable, so that's and that's t. So we can say that we know this is a first order. Oh, we hadn't talked about first order yet. How do we know about first order? We know it's first order since what? We talked about this last time, right? Since the highest derivative is v prime, right? The first derivative. So this is a first order constant coefficient linear non-homogeneous differential equation. All right, so make sure you can see all of those pieces before moving on. If we look at the pump problem, right, or the chamber problem, where we had either the salt tank or the cochlear implant. We had what? RC1 minus RU of t all over V. And so here we knew, some things here. Well, we see it's first order, right? We can see it's linear because U only has a power of 1 here. Linear. We can see it's a constant coefficient because R, the flow rate, and V, this piece here, R over V, this is constant because the volume of the tank is fixed, or the chamber, and the rate of flow is fixed in this example, right? So we know this is constant coefficient. And we know that this is non-homogeneous because we have a forcing term here. We have an input. Differential equation, ordinary differential equation. And again, we said in the first lecture that these are really the same equation. Just the parameters are slightly different, but the math that governs them is exactly the same. So we'd expect them to be classified exactly the same, right? So that shouldn't be a shocker. So the third one, which I don't think we had a chance to look at together yet, is the logistic equation. And I believe I encouraged you to read about this. And the form of the logistic equation is as follows. You've got some unknown rate, or the rate of the unknown function, rather, is equal to the rate of growth times u times 1 minus u over k. And if you have a harvesting term, then this is h times u. So this is with the harvesting, okay? So to see this a little bit better, it might make sense to rewrite this a bit. We'll see if I distribute the RU through, we've got RU minus RU squared over K minus HU. We know that R, H, K are constants. Okay. So here, what do we know? Well, we know it's constant coefficient, right? Because the u terms have constant coefficients. We know that it's first order because the highest derivative we see is first derivative. We see that it's non-homogeneous because there is actually there's no forcing term here, so we don't want to classify it as that. Interestingly, this is an example of an autonomous equation, which we'll be looking at in a little bit. So this is not non-homogeneous. This is autonomous, meaning it doesn't depend directly on t, but don't worry about not understanding what that means. It's first order, but is it linear is the question. It is not linear because you're seeing this power of 2 here. Okay, so it doesn't have to be 2. It could be a rational power, but anything that's not a power of 1 makes it non-linear. So this is a non-linear equation. Still ordinary. Differential equation. Okay, so just a little bit of practice identifying the pieces here, these basic terms. All right, so you might think, based on this, you've seen derivatives and things before. You might feel like you've got this. Just integrate. You're good to go. Integrate both sides. So that works for the simple ones we saw in the last section, right? As long as you know what the antiderivatives are and the equation is in such a way that you can just integrate on both sides. However, let's take a look in general. Let's take a look at the form that we've been given. We write this as a linear first order equation, right? Again, if you can write it like this, that means it is of that form. So if we go ahead and just try to integrate both sides, it's like, just do it, Mally. Why stall so much here? Well, on the left, we'd of course get the antiderivative u of t, maybe a constant of integration. And on the left, we'd get, well, let's just slow down here, g of t plus h of t, u of t dt, and then we'd have maybe our second constant of integration. So I would need to know what u of t is in order to integrate over here. And this is precisely the problem. Okay, this is what makes it more challenging. So, we kind of got to hit the brakes and say, how do we deal with this? Well, the answer lies in being a little bit creative and actually understanding very clearly the rules of differentiation and integration. All right, so let's, by way of example here, look again at the Hill-Keller model. We knew it was v prime is what? P minus k times v of t. And what we can do, maybe assume that v of 0 equals 0, even though we know this doesn't really fit the data that we have, just to simplify things if we solve the IVP. But really I want to go after the general solution here. So the first thing we do is get into a standard form for solving. And that's to bring this kv term over to the left. So we'll have v prime plus kv of t equals p. All right, this is more what we consider to be a standard form. Now, the next step here might seem like a bit of a shock, but what I'm going to do is multiply both sides by e to the kt. Okay, why is this the case? Well, you'll see in a moment. All right, I'm going to multiply both sides by e to the k times t. And so I'll write it like this so you can see what I'm talking about. On the left, since I'm a, avid calculus practitioner, I see, hey, v prime plus something times v, that looks like it came from the product rule, maybe? And so, what must this have been if it came from the product rule? Well, we notice that when I take the derivative of v times e to the kt, what are we going to get? Well, we'd get, v prime times e to the kt plus what? K times v times e to the kt. And doesn't that look a heck of a lot like what we've got now, this e to the kt times v prime plus kv? So this is where that recognition is kind of the key, and the only way that we can unlock this solution is noticing, all right, this must have come from this derivative of this product of functions. So then we can rewrite the left then as this. Well, this is really the derivative of e to the kt times v of t. And on the right-hand side, we've still got p e to the kt. Okay, got pulled away for a second there. So where were we? So we got that the derivative of the left-hand side is equal to the right-hand side based on recognizing, hey, this must have come from the product rule. So that way, we can now apply the only kind of way we know how to solve DEs at this point, which is to integrate both sides, right? So we'll go ahead and integrate the left. I'll just be left with e to the kt times v, right? And then I'll integrate p e to the kt dt over here, noting that I'll have a constant of integration. Actually, when I slow down and say, remember, we're going to have a constant of integration over here, and we'll have a constant of integration over here. Oops. Have one after we carry out this, but that's okay to put it there for now. And so then we'll have e to the kt. If I combine these constants, right, they're constants of integration, I can't really be too flippant about it, but we can be, as long as we do some bookkeeping, we can be relatively irresponsible with these. So we'll just say, all right, our new c is just c2 minus c1 as I bring that over here. So e to the kt times v on the left is equal to integral of p e to the kt. Remember, k is a constant. This is really just p over k e to the kt plus that constant c we just defined. And then from here, I'm going to move to the next page. All right, so I have this expression on the left and expression on the right. I'm trying to solve for v, right, our unknown velocity at time t. And so how I do that is multiply both sides by e to the minus kt. It's the same thing as dividing, right, by e to the kt. But this just simplifies our algebra a little bit. So the left-hand side will simplify to just v. The right-hand side, distribute e to the negative kt. You'll just be left with p over k, because that becomes 1, plus c e to the minus kt. Okay, and this is what we call our what? Our general solution. Why is it a general solution? Because it depends on a constant c. This is a family of functions. So it's actually infinitely many functions that that solve this equation. And now if we had our initial, condition for a particular solution that we care about, we said our initial condition was v of 0 equals 0. Then this tells us that, v of 0 equals 0, which is p over k plus c e to the minus k times 0. E to the 0 is just 1, so this tells us that c must equal negative p over k. All right, so then our particular solution, then you can call it vp of t if you want to, is p over k minus, instead of plus c, it's minus p over k e to the kt, negative kt. So again, p and k can be derived from data, but this would be the particular solution to this dE. Okay, so just to kind of recap, what did we do? We looked at this equation. We saw it was of this form that, if I integrated both sides, it wouldn't really quite work out. So we used this e to the kt, which we call the integrating factor. Because this allowed us to pretend as if the left-hand side had come from the derivative of some product. We got the right-hand side into a form that was integrable, and then we integrated both sides and then divided by the appropriate piece to result in a solution that looks like a function of time. Okay, and a quick note to follow up on like the dimensionality that we discussed, which is that, P, that propulsive, so this propulsive piece, what were the units? It was, the units of acceleration, which was, Lt to the minus 2. And the units of k, which come from the data from this model, we know that the units of this were the inverse of time. So, 1 over seconds or 1 over minutes, whatever it might be. So we can see that with the units on the left, for velocity would need to be length 1 t minus 1, length per unit time. Then the right-hand side will also work out. Okay, so that is a very good thing. Again, and another way you can think about it is that, k needs to kind of make this interior piece dimensionless. So it needs to balance out the time that's going inside. So that's why it's 1 over t. Okay. All right, so what I'm going to do is I'm going to pause here. I'm going to create a second video that will outline the general procedure here now that you have the motivation for this method. Then we'll have the method kind of in its own section that can be referred to. And then we'll jump into some examples.